So welcome back again in continuation of our earlier reading. The name of article is electrically tuned fractional order temporal differentiator in silicon photonics. So in order to have continuity, let me read the abstract portion again. Here, full wave analysis and design of an electrically tunable optical fractional order temporal differentiator based on an ultra compact micro ring resonator has been presented. Electrical tunability has been realized through free carrier dispersion effect in the resonator with PIN and PN junction. The first order optical differentiator is realized based on the critically coupled resonator without applying any bias voltage in the junctions. Also, fractional order differentiator with differentiation order alpha greater than 1 is realized by over coupled resonator with forward biased PIN and PN junctions. While fractional order differentiator with alpha less than 1 is realized by under coupled resonator with reverse biased PN junction. The high performance of design tunable optical differentiator and their high accuracy have been confirmed considering an ultra fast Gaussian input pulse with short full width at half maximum of 6.3 picosecond. So this is the abstract, and we left last time. We read this introduction portion, then full wave analysis of temporal differentiator in the frequency domain by taking Fourier transform, then photonic micro ring resonator. Its structure we have seen PIN and PN, and this is electric field profile, then transfer function, and symmetric and asymmetric modes, and then the three-dimensional profile of electric field in APM all pass MRR. APMRR in its critical coupling region. In critical coupling region, no output is available. And now we have to start today from 2.3, that is the electrical theory. Variation of carrier concentration in forward and reverse biased PN and PIN junction have been simulated by numerical device which solves the Poisson's equations and the continuity equation, charge continuity equation using a finite element method. So Poisson equation, Laplace equation. Two equations are there in Laplace equation. Del dot V is equal to 0. However, in Poisson, del dot V is equal to some rho. So because there is some charge. And charge continuity equation consists of Drude diffusion equation. It seems to be. And these two equations have been solved using finite element method on numerical device. So these are the some curve. Just before going forward, we will just scan. Intensity transmission A, this image A is intensity transmission, A, C, and phase response B and D. So A is here, up, this one, and C, this one. So this is the intensity transmission. Here you can see intensity versus frequency. Here intensity versus optical frequency. So, but first one should be A and C. Both are A and C are both are intensity. And phase response are this one. Phase response, this and this of all pass micro ring resonator for different voltages in the PIN junction. So here different voltages, voltage equal to 0, voltage equal to 0 0.65, 0 0.75, these are 3 voltages, and these are the plus voltages here now. The second one, 0 volt, again that V is equal to minus 6, 0 0.65, the third one is the minus 0 0.75 voltage, and the structure is PIN. So This is the PIR. The insect shows the effective refractive index of the desired mode in the region, right? As a function of rapid applied voltage. So this is the insect. This voltage versus effective refractive index. We are part of the effective refractive index, and this is here for negative voltage, so constant. However, for positive voltage, there is a drastic decrease in the value of effective refractive voltage. Similarly, same thing goes here. Phase response. So this is a imaginary part of effective refractive index, voltage, positive voltage, and then negative voltage, and phase response. So suppose this is a for same configuration, it seems to be, because these both are for positive voltages. So this and this for positive voltages, and this for this C and D for negative voltages. So amplitude response and phase response. So here you can see for negative applying voltage, there is no shift. Electric shift we can observe in the negative potential. For positive, no. And phase response, yeah, for negative, you can see change in the phase response, whereas there is no change in the phase response with respect to change in the negative voltages applied at PIR. And second one, intensity transmission AC and phase response BD of APMRR for different voltages in the PN junction. So earlier it was PIR, this one, and now second one is the PIR. The insect shows the effective refractive index of the desired mode in the region, right, as a function of the applied voltage. So this is the insect voltage versus effective refractive index for positive voltage applied, negative voltage applied. Or positive voltage applied is here, so negative voltage applied is here, and negative voltage applied here. This is intensity transmission. This is phase response from 0 to 2 pi. And intensity transmission minus 40 dB to 0 dB. So this is the transmission. So okay, for here. The third base, which is shown here, that is the figure 10, phase response of APMRR with PIN junction for bias voltage of A 0.65 voltage and 0.75 voltage, and the positive voltage together with phase response of mathematical differentiator with a differentiation order of alpha is equal to 1.3 and alpha is equal to 1.45. So here we can see optical frequency phase response. This is also phase response. The optical MMR, this is mathematical differentiator. Alpha is equal to 1.3. Here alpha is equal to 1.45. So you see here, red curve is shown optical MMR. Mathematically is dash 1. So mathematically it should be like this. Case of phase change is there from this value to this value, which is which we can observe in the optical MMR also. The second one also for 0.675 voltage, this is 0.65 voltage. That the result of numerical device have been imported to numerical FDDT in order to calculate the variation of real and imaginary part of the refractive index based on Soren-Barrett formula, that is plasma dispersion effect. Variation of the intensity transmission and phase response of all pass MRR considering different voltage applied in the PIR and PN junctions are shown in figure 8 and 9 that we have seen respectively. According to inset shown in figure 8AB, the real part of the effective refractive index increases by increasing the forward bias voltage from approximately 0.65 voltage to 1 volt. While its imaginary part decreases by increasing the forward bias voltage. from 0.65 to 1 voltage. Okay. So there is increase in the voltage, but there is a decrease in the effective refractive index, while the imaginary part increases. Okay. Decrease of the real part of the refractive index leads to a blue shift in the resonance frequency of the AEMR. Blue shift is here. We can see 8AB. So we can go 8 and B. This. So you should mean there is a increase in the frequency. You can see voltage is increasing, so the resonance frequency is shifting towards the right. So frequency is increasing, means wavelength is decreasing. So decrease in the wavelength is blue shift. This is what we can observe from here. While increasing the imaginary part of the effective refractive index causes to wider 3 dB bandwidth. These phenomena have been illustrated in figure 8b. Also, according to figure 8b, all optical RR with PIN junction migrate from the critical coupling region to overcoupling region by applying the forward bias voltage. Therefore, the first order differentiator is converted to a fractional order differentiator with alpha is greater than 1. So critical coupling to overcoupling. So this is what is called fractional order differentiator with alpha is greater than 1. It should be noted that in this case, the phase shift in the reverse phase response increases by increasing the bias voltage, which represents increasing the differentiation order alpha. So this is state B. So this where we critical coupling to overcoupling first order. So 8P, let us see 8P response. So critical coupling to overcoupling, if we increase this voltage, increase the voltage, this one. Okay, so this is a fractional order. Here 0.65, 0.75. This is 0 voltage by differentiator. So change the phase. Okay, from 0 to positive to negative. Similarly, all phenomena shown in figure 8b can be shown in figure 9ab for the same APMRR with forward bias PN junction. So forward bias PN junction this A and B. Of course, because positive voltage is applied, so this is forward bias case. So this is also blue shift in case of PN now in fractional order. Of course, variation in this case are stronger. As a significant result, the same order of fractional differentiator using the forward bias voltage can be realized in the PN junction utilizing low voltage compared with the PIN junction. However, it should be noted that the most change of resonance frequency can reduce the accuracy of differentiator. This subject will be investigated in detail based on the results shown in figure 11 and 15. The insect depicted in 8CD show the reverse bias PIN junction cannot change significantly the effective refractive index. Now 8CD, so 8C and D, here we can change. There is no change in the effective refractive index with respect to changing the voltage. So here also, so reverse bias not possible. You can see there is no change in the phase, there is no shift in blue shift or red shift. So yeah, reverse bias, because applying the reverse bias voltage leads to an increase in the width of the diffraction region. As a result, the effective refractive index cannot change significantly due to negligible variation in the carrier concentration. So this is called reverse bias. Okay, reverse bias PN junction. Yeah, reverse bias PN junction is not applicable for PIN. It is applicable for PN. So that this variation can be ignored. Consequently, as in figure 8CB, there is no considerable change in the intensity, transmission, and phase response curve. Therefore, the reverse bias PI injection is not useful candidate to design tunable. Okay, so reverse bias. Yeah, that too we know because the carrier plasma dispersion effects occurs more in forward bias in case of PIN. However, in reverse bias is for PIN injection. So this is where so we can see here also forward bias by C line and D. Oh, no phase change here. Not as such bullshit. Reverse bias also. But forward bias, yes. So moving ahead, finally, according to his sets shown in figure 9CD, the real part of effective refractive index increases by increasing the reverse bias voltage, while its imaginary part decreases. This variation can also be interpreted by Soref and Bennett formula. Increasing the real part of effective refractive index leads to a red shift in the resonance frequency of the PMRR, while decreasing of its imaginary part causes to narrower 3 dB bandwidth. These phenomena have been illustrated in figure 9C. Also, according to 9D, APMRR with PN junction migrates from the critical coupling regime to the undercoupling regime by applying the reverse bias voltage. Therefore, the first order differentiator converts to a fractional order differentiator with alpha less than 1. It should be noted that in this case, the phase shift in the phase response decreases by increasing the reverse bias voltage, which represents decreasing of differentiation order alpha. In order to comprehensive analysis of design to enable fractional order differentiator, the phase response of the APMRR based on PIN and PN junction for different bias voltages are compared in figure 10 and 11 with those of the mathematical differentiator. According to figure 10, there is a good agreement. Between phase response of a overcoupled APMR based on PIN junction with the phase response of associated mathematical differentiator. This is due to the little change of effective refractive index with applying forward bias in PIN junction shown in figure set 8AB. Also, the phase shift in the reverse bias response are equal to 1.3 pi and 1.45 pi respectively by applying bias voltage of 0.65 volt and 0.75 volt. Therefore, the designed APMR is a tunable differentiator, respectively the differentiation order of 1.3 and 1.45. It can be concluded that the differentiation order alpha is increased in this case with increasing of the forward bias voltage. According to figure 11AB, it can be concluded that unlike the PIN junction, there is a good agreement between the phase response of overcoupled APMRR based on the PIN junction with the phase response of the associated mathematical differentiator for all applied forward bias voltage. This is due to the considerable change of the effective refractive index with applying forward bias in PN junction shown in the inset of figure 9, especially for high voltage. Therefore, the forward bias PN junction is not suitable device. Forward bias, yeah, that is okay. To realize a fractional order differentiator with high differentiation order, especially 1.45 less than alpha less than 2. This subject will be investigated again for the results shown in figure 15. So, however, the accuracy of the result obtained for APMR applying for the forward bias PN junction is good for lower voltage. Also, the same order of fractional differentiator using the forward bias voltage can be realized in the PN junction utilizing low voltage compared with the PIN junction. In other words, considering same low value for the forward bias voltage in the PR and PI junction, a high differentiation order alpha can be realized by the PI junction. Finally, according to figure 11, there is a good agreement between phase response of the undercoupled APMRR based on reverse bias PN junction with the phase response of associated mathematical differentiator. This is due to the small changes of the effective refractive index shown in the set of figure 9CD for reverse bias PN junction. Also, the phase shift in the phase responses are equal to 0.95 pi and 0.55 pi respectively by applying bias voltage of -8 volt and -0.5 volt. Therefore, the desired APMRR is a tunable differentiator, respectively with differentiation order of 0.92 and 0.55. As illustrated, the differentiator order alpha is increased with increasing of the absolute value of the reverse biased voltage. Since the reverse bias PIN junction is not a useful candidate to design of a tunable differentiator, our only proposed CFT-based device to realize a tunable fractional order differentiator with orders of alpha less than 0, actually alpha 0 greater than 0 less than alpha less than 1 is the reverse bias PIN junction. This fortunately is an efficient option. So, thank you very much for attending. Next session we will start from the reading section 3, that is the full wave analysis of temporal differentiator in the time domain.